In the previous videos, we're able to establish the definition of subsequences and also shown a certain proof of this subsequence convergence theorem, which tells us that again, if a sequence x sub n of real numbers converges to a certain limit x, then any subsequence of that sequence be indicated by this, or if you could have more than one, they're all converges to the same limit x. We are going to illustrate this using some examples. Okay, so let us have here example of a sequence. Let's say our sequence x sub n is a sequence of 1 over n. Okay, so first let us identify whether this is convergent and the value of its limit, and later on identify subsequences of this and show if those subsequences also converges to the same limit. Of course, we know that if we try natural numbers n, you will have here 1, 1/2, 1/3, 1/4, 1/5, 1/6, so on and so forth. Okay, so with this in mind, of course, some of us can already identify whether this is convergent or not, but we can see here that its value, our supremum, okay, of x sub n being the least upper bound is the value of 1. And when you look at this certain sequence, you could identify the infimum, okay, of this sequence being the greatest lower bound. It may not be present as part of the sequence here, but we could see that as n approaches infinity, the limit of this is actually equal to 0, and that is also the infimum of our sequence. Okay, since this is considered to be the lower bound, and this is also the upper bound of our sequence, we can say that our sequence is both bounded below and bounded above. This means that our sequence is bounded. Okay, and by monotone convergence theorem, okay, and by the way, we are using that because we could guarantee here where the elements here follow a certain trend. We can see that this is an example of a decreasing sequence, hence again it's monotone. So since it's a monotone and it's bounded, given by monotone convergence theorem, this sequence is also convergent. Okay, and simply using the idea of the monotone convergence theorem, we have the second statement there that if it is a bounded decreasing sequence and again identified as convergent, the limit of your sequence is equal to the infimum of your x sub n, set of x sub n, as n is any natural number. And since the infimum is 0, the limit here is 0. The limit of x sub n is 0, and this is also the value where our sequence 1 over n is converging to. So take note of this because this is what we're going to show also as well for any subsequence. So take note that for this video, we're trying to combine subsequence convergence theorem and the previously discussed monotone convergence theorem as well. Okay, that's for the sequence alone. Take note that this theorem talks about subsequence. So looking at this, we can identify our first subsequence where we pick our n being even. So n sub 1, let's say 2, n sub 2 is 4. Let me also use here n sub 3 is 6, n sub 4 is 8, n sub 5 is 10. So the element or this sequence, subsequence x prime, you will have here 1/2, 1/4, 1/6, 1/8, 1/10, and so on and so forth. And this is considered to be a subsequence of our x here, where all of these are also elements of the sequence. Or if you would like to, your x prime could also be denoted as this 1 over twice n. Okay, as you will use n being equal to 1, only not these values, you will also have the same entries. So if you would like to do to have this, that's okay, or you're going to have this process here, but both of them will have the same value. Just for the purpose of discussion, okay, let me remove this and use this definition, okay, so that we could see that this is another sequence, but it's a subsequence of 1 over n. And basically they have different what they call this one elements, but this is a subset of that sequence there. So it tells us here that if we could find subsequence of any sequence, it should also converge to x, where it is the limit of your sequence, and that is actually 0 here. Let's show that this is also converging to our limit of 0. Again, for the purpose of review as well, let's use the previously discussed theorem as well. Of course, you can identify it here that this is actually bounded. It's obvious to be bounded because you can see here that the supremum of your x sub n being the least upper bound, that's actually 1/2. The infimum of your x sub n here, which is your greatest lower bound, though it's not part again of this subsequence, but it's actually the limit, okay, the limit of this sequence as n approaches infinity, it's 0. So it's bounded, okay, and as you can see, it's also monotone, as we will have decreasing sequence here. So it's bounded, it's monotone, hence by monotone convergence theorem, this is convergent. Okay, so since it's convergent, we can use the statements of monotone convergence theorem. It's either A or B, but since this is decreasing, we'll be using B. As the same thing here, the limit of your x sub n is the infimum of the set containing x sub n, where all n element of natural numbers. And since the infimum of your sequence is 0, so you also have the limit of 0. So you can see the limit of your subsequence x prime is 0 is the same as the limit of your sequence x. So this supports the statement of your subsequence convergence theorem, and this illustrates further that they also converge to the same limit. You could also have another subsequence here, let's say double prime, and let us use here 1 over n squared. Okay, this contains the elements where n is 1, so you'll have 1, so you have 1/4, 1/9, 1 over 16. Okay, and obviously this is really a subsequence of x, as if you're going to move this further, you will have also 1 over 9s and 1/16 as well. And similarly, you will have here, this is bounded, your supremum, sorry, I am using here x sub, let me use prime just so that you will not be confused. Okay, so double prime here, so you have 1, the greatest, the least upper bound. Your infimum is again is 0 as the limit of this when n approaches infinity, and then again it is bounded, as it is bounded below and above. This is monotone, as you can see for the elements here decreasing in order, hence by monotone convergence theorem, this is also convergent. And since it's convergent and it's a bounded decreasing sequence, again the limit of this is also its infimum. Okay, so we are repeating all of this so that it would be considered to be also a review to the previously discussed theorem. So it's still 0, which is just the same as the limits of the first subsequence and ultimately the sequence itself. So again, this is how we illustrate this, and this is true. We have proven this, and we have also illustrated this theorem using these examples. Thank you very much for watching.